everyone. Thank you very much for joining us today for our webinar on RF fundamentals. This is part 2 of our 3-part series. Before we get started, I'd just like to let everyone know that this webinar will be recorded and you will be receiving an email afterwards with the recording, so you can go ahead and share it with anyone you think would be interested or rewatch it if you'd like. As you know, this is a 3-part series on RF fundamentals, and for your information, you've automatically been registered for part 3 as well, and you'll be receiving reminders and login information for the next webinars a few weeks in advance. If you're interested in any of the other webinars we'll be hosting, or to download any of the other free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy, and you'll find everything you need right there. If during the webinar you have any questions, make sure you ask them in the Q&A section in the right side menu bar, and we will be sure to get to all of those questions as we get to the end of the presentation. And now, without further ado, let's jump right in where we left off last month and talk about RF fundamentals with Neil Jarvis.
So now we're going to talk about, see, this says this is fun, so if you weren't having fun, I'm sorry. Anyways, RF transmission characteristics, RF fundamentals, and I didn't make that up, so. Okay, so we're going to talk about transmission, some measurements, and some components. Already gone through the whole schedule. So wave propagation. So we talked about free space. I'm going to wander down here for a little bit. So free space in air, all intensive purposes, or transmission lines. So we were talking about propagation through space, but transmission line. Obviously, this is like on my PCB or my whatever my device is. Could be a component or whatever, where I'm trying to direct where that thing's going, and it's going to go through some components and whatnot. So this isn't simply a wire, right? So if you've done any kind of transmission line design, so even like digital guys, you probably have had to make a 50 ohm line, or in some cases 100 ohm differential pair, or there's some weird ones like 70 or 90 ohms, and I'll kind of mention that in a little bit. But transmission lines. Okay, so some of the more common transmission lines you'll see in the RF world, parallel lines. So this is, this is showing a wire, but it's really more like a twisted pair or something like that. Parallel lines, coax cable. This is kind of the most common thing you're going to see as an RF microwave kind of person. Even high-speed digital really now too. This is more like what you'd see on a TV type thing. Microstrip lines. So this is, if you're designing circuit boards. Anybody here design circuit boards? Okay, I see a few of you. Like more high-speed digital, or what kind of stuff are you doing?
Mixed signal.
Mixed signal. Okay, good. Anybody else? What do you do? PA. All right. We like. I like PAs. Okay, so anyways, so microstrip line, so that's a transmission line on a board, and there's different variants of that. That's a transmission line single by itself, but then you can also have what's called a coplanar waveguide, which is a similar thing where the ground planes are more closely defined to maintain that and reduce the fringing effects. Then you have waveguides, and this is typically much higher frequencies. So this is getting up, usually, 20, 30, 50, 70 gigahertz kind of thing. But interestingly, I was at I had a customer I was doing interference hunting, and the customer was AT&T. So we were out looking for somebody interfering with their base station, and it was actually an FM station was going onto the cell phone network. So the guy I went out with, we went out there and we went into a radio rack for a FM station, and they had just like big copper pipes, because they do really high power. So you can buy copper pipe that's the right dimensions to make a waveguide. So that was kind of interesting to me. Okay, so why do we have different types of transmission lines, power handling. So one of the nice things with waveguides is they're very, very low loss. Close to zero, actually, for a good waveguide. Frequency, what frequency they operate over. So it's kind of some of the key things. So what are some of the basics? Well, obviously you have a source and a load. So this might be an antenna. This might be my transceiver, right, or my transmitter. So I need it to get from there to there, right? So I design a transmission line, probably a 50 ohm line. Okay. In this case, it's a coax line, right? What does it look like? There's an interconductor, there's a dielectric, there's an insulator, and there's a shield. Okay, so really, some people, like purist guys who do signal integrity, won't call that ground, they'll call it return path, but same difference. So anybody, for a prize, where does the current travel? Surface, good. And how much does it, and how does it change as frequency goes up? What's the difference for a higher frequency versus a lower frequency? Okay, so it's going to get, what do you want? You want a book? Okay. I got to get rid of this stuff, so. Okay, good. So it goes on the surface. So that's why you'll see a lot of times on transmission lines and more expensive cabling and stuff where they actually just have a thin layer of gold on it, right? Okay, so wavelength, I kind of talked about that, but it's really the distance for one period of a sine wave. I guess it doesn't have to be a sine wave, but anyways. So it'll continue on. Maybe you hit some obstruction. So in this case, we're talking about a reflection, right? So that signal is now bouncing back. So in the case where you had asked me, how can you have a signal bigger than what you sent? If you have, if these were in phase, that would get bigger. In this case, they are out of phase, so you could actually have almost nothing if they were perfectly out of phase. That doesn't usually happen, but you might have close to out of phase 180 degrees whereby the signal would be dramatically attenuated. Okay. They're typically designed to transport a signal along an axis, right? So one thing, just a cautionary note, often you need to turn when you're using a cable or a transmission line. Avoid right angles. You know, I've seen stuff where they actually measured like current density on some instruments, and you'd be amazed how much things change when you take a sharp turn. So it really degrades the performance a lot. So try to avoid that. Just think of it like flowing like a pipe, really. Okay, quarter wavelength. So quarter wavelength makes a good antenna, right? So if you have a stub of a transmission line on a board, and you probably know about this, that can make that thing radiate more. So you've got to be really careful about the lengths of lines that you make on a transmission line. Okay, so this guy who made these originally likes these little tables, but here's some examples of frequencies and wavelengths. Obviously, unless you're European, the outlet on the wall over there, that's 60 hertz. That's the wavelength. Obviously, that's a big number, right? So if you wanted to make an antenna that worked over there, it'd be big. You know, even if it wasn't a quarter or half wavelength, but some smaller integer, which you can still do, but it's not very efficient, it would still be big. Human voice, 2 kilohertz, AM radio, blah, blah, blah. Did somebody ask me? Oh. So direct TV, you can see, is 11 gigahertz. Okay, and there's just some numbers somebody came up with. So here's the quarter wavelength or antenna size, telling you how big some things are. So Wi-Fi, etc. EMC chamber. So this is like when you want to measure the emissions from a device and you want to make sure nothing else gets in. We make those too, believe it or not. Anyways, so wavelength versus line length. Okay, low frequency. So typically this is, I was talking earlier how there used to be a pretty significant delineation between an analog or digital engineer and an RF microwave engineer, where most people used to be operating here. So if you look at the wavelength of this relative to the size of the transmission line, even on a board or whatever, it's much, much smaller. So you just make the assumption that the phase stays the same over the transmission line, which was a good assumption. But as you've gone up in frequency, the wavelengths get shorter and they get more closer to the dimensions of the device. And that's where you kind of get into more RF microwave type effects. You have to worry about the characteristic impedance and things like that. Sorry, I like to wander a lot. Okay, so back to transmission lines. So typically parallel lines, you'll see this is kind of like speaker wire, for example, or even your plugs, right? Those are 60 hertz. You don't really care about the impedance changes along the line. You're just looking for a conductor. Microstrip line, and these are really things on circuit boards. Like if you looked on your cell phone or your wireless LAN or whatever, you would see lots of microstrip lines or things, microstrip type lines. If it's, incidentally, if it's a buried microstrip line, that's called a strip line. Okay, coaxial cable, high bandwidth, easy to use, right? You screw them on. That's kind of like your TV antenna, things like that. Waveguide, really high power. So like, for example, I did, when I was looking at that transmitter station, they're all waveguides. Because a lot of stuff, if you get into like kilowatts, megawatts or something like that, and you put that into here, it'll just vaporize it. So that's why I use a waveguide. Okay, I got to give some prizes down here, so. Books. All right. Keep everybody awake. Okay, so let's see. Transmission line, waveguide. So this is talking about, these are some of the waveguide bands, and I would find it unlikely most people here would probably ever deal with these. But these are some of the different types of waveguides. This is the bandwidth. So, waveguides act like a bandpass filter. So when you get outside the bandwidth of that waveguide, it pretty much doesn't pass anything. So, and there's the band names. So again, these are more often than not, they're used by satellite people. They like those band nomenclatures, and they do high power too. Okay. Okay, so it's an easy one. So what's the typical characteristic impedance that I mentioned earlier for a book? 50 ohms. Okay. So all transmission lines have some power loss, probably heat. Okay, and when you have a transmission line, typically you're not going to get a reflection just for no reason. Usually transmission lines, be it a PCB or a cable or a waveguide, typically along the transmission line it's very uniform and you don't get reflections along the line. It's when you get to a transition. So maybe that thing has a connector on it, right? And so when you get to the connector, then you're going to get a reflection at the connector. People like to use lots of adapters and things, and you have to use what you have to use dependent on the instrument. But realize every time you put a connection in there, you're degrading the standing wave ratio of your device, so you're going to get more reflections. So when you see stuff, I've seen stuff where they have like 6 things all bunched together, and if you went and looked at that on a VNA, it looks horrible, right? And you can't just cal it out. People like to think that, but it doesn't work that way. Okay. Effects of dielectrics. Okay, so effects of dielectric. You know, the bottom line is the speed of propagation through a dielectric medium is obviously different. Question?
Are you saying like those N adapters to SMA?
Uh-huh.
Those are bad?
I'm not saying they're bad. From a purist point of view of does it degrade the signal, it absolutely does. So from that perspective, it's bad. But you obviously need them, right? I need to plug into my spectrum analyzer. Hopefully you have a spectrum analyzer. And you need a connector. But my point is more, you'll often see where somebody, maybe they have a SMA cable from their whatever, and then they connect it to like a BNC, and then the BNC connects to another BNC, which connects to an N, which goes to the instrument. Every interface there is degrading the standing wave ratio. So you're getting reflections in there from each of those connections. So when you do it, it's A, use really good connectors, you know, if you care about this, and B, minimize the number of connections, right? So don't, if you have an SMA and you need to get to an N, get the right adapter, right? Ideally get a cable that has the cable right to that interface. That's really more the moral of the story. Yeah?
Can you characterize that through the S parameters?
You can, but you can't remove it, right? I mean, it's there. So when you do it's sort of like a noise floor thing, right? If you say, and I get this all the time, so if you get a bad cable and you say, okay, I want to measure all my S parameters of my device with a bad cable, and then I look at a good cable, after you've done the calibration and you look at where is my residual S11 of my cable at the calibration point, you might find with a bad cable, and I've seen this, it might be 20 dB, right? That's as good as it's ever going to get. Then you go and get, you know, a Goreflex, air dielectric, blah, 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 and now it's 40 dB after calibration. So, you know, the key thing to remember is you can vector correct it, but you're more or less establishing a noise floor based on the worst case VISWAR of whatever is in there. It's a great question, though. Okay. So measurements. Okay, so anybody, for a prize, what instrument would I use to measure this kind of stuff? Okay. You gotta raise your hand. All right, I'll give it to you. Book? You want a book or you want something else? Book. I'm gonna run out of books soon. Here you go. Okay. And incidentally, my number one thing I support is VNAs, so I like to talk about VNAs. So all this stuff where you see reference planes, and I'll talk ad nauseum about this, so bear with me. Okay, so reference plane. So after you do a calibration with a VNA, you're really establishing this reference plane. And it's one of the cooler things about a VNA is, you know, most instruments, you don't get to kind of pick where you measure. You know, the front panel of that device is really your measurement reference plane. You can add losses and things like that to it, but it's not really designed to automatically figure that out for you. That's what's, to me, really cool about a VNA. Okay, I'm a nerd, so bear with me. Port 1 and port 2. So this is all VNA stuff. So fundamentally, in a VNA, it measures S parameters. Okay, so don't let anybody tell you otherwise. It measures S parameters. All the other stuff, it basically takes those measurements and it manipulates them mathematically to get other stuff. So after I do it, I get S11, S22, S21, S12. So 1 and 2, that's basically the reflected at port 1. 2.2 is the reflected at port 2. So obviously you get a mismatch anywhere. Okay? S21 is if I'm going this way forward, that might be the gain or loss of my device. But then you sometimes have cases where a signal goes in the wrong direction, right? So in the case of, say, I have a power amplifier and it's connected to an antenna. If somebody breaks the antenna, and you've seen that in the old car radios, right? I don't think they have whip antennas anymore on cars, so I'm dating myself again. But like somebody would break your antenna, and maybe your car wouldn't work or whatever. But on the transmitter side, that's a much bigger deal because it could be a huge signal, right? If you remember like the FM AM radios, it was like a kilowatt, right? If you put that kilowatt into an open where all that signal gets reflected, if it wasn't designed to handle it, it'll just vaporize everything, right? And so like we have customers who do that with VNAs, and it's great because we get to sell them another VNA. So or they have to fix it, and it's not my fault. Anyways, so all these other things we can measure with the VNA. Again, when I do a calibration, I'm going to establish my measurement plane at these two ports, right? So that's establishing a phase of 0 and an amplitude reference of 1. So anything I put between those two things is what I measure. So that's kind of a pretty cool thing that's unique. So we can measure phase, insertion phase. That's what's the phase response through here. Group delay, return loss, whatever. Impedance, things like that. Okay, so some of the different reflection measurements. And I'm sure there's other people here who do signal integrity kind of stuff? Not a single person. You're full of blank. I don't believe you. Okay, I would have given you a prize, but... Okay, so reflection. So, when you're measuring a reflection, you're really measuring how much of that wave bounces back from my mismatch. Okay, so when I do that, there's different ways of representing that mathematically. And depending on who you talk to, different people have different nomenclature, as you all well know. So, you can tell it, I want to look at the reflection coefficient. I can look at return loss. I can look at VISWAR, all kinds of things. But they all really are measuring the same thing. So, no reflection, good. Full reflection, bad. Okay, so some of the different metrics for reflection coefficient of 0 is perfect, and 1, plus or minus 1, depending on the phase, is fully reflected. And then return loss of 0 is basically fully reflected, et cetera, et cetera. It's very hard to achieve these numbers, right? The guys typically that I see that come the closest to these are guys who do satellite stuff, who really don't care how much stuff costs. I mean, that's a somewhat tongue-in-cheek, but they'll spend a lot of money because they're going to put a satellite in orbit for 10 or 20 years, so that thing better work. It better be really good, and it better be efficient over time. So anyways. Okay, so when we're talking transmissions, so this is going through the device as opposed to reflecting. Okay? So there's transmission coefficient. I don't really see that all that often, but, it's a thing. Insertion loss or gain, right? This is typically passive devices, lossy devices, and this is more typically active devices. More amplifiers than anything, but there's active mixers and things like that. Okay. So, looking inside a VNA, so now we're taking a VNA apart. To measure these measurements, the key things that I need to have, I need a source, I need at least one coupler, probably two. In this case, I have two. I need measurement receivers. Okay? So basically what happens, I stimulate my device. So if this is an amplifier, for example, I send a signal in. It samples the signal as it goes out. So I measure the amplitude and phase here. Then some signal gets reflected back here, and I measure it here, amplitude and phase. So when I measure S11, I'm just doing a ratio of these two things, right? So when I do a calibration, without getting into a lot of detail, I'm going to put known things right here, and then connect them between. So when I connect it with a cable on, I kind of know exactly what is supposed to happen, and it'll figure out what's going on between the front panel of the instrument and wherever you connected that standard. So, you know, if you use, did anybody here use a VNA? Okay, good, lots of hands. Good answer. My people. Anyway, so, you know, in the olden days, if you have enough gray hairs, that when you did that calibration, you had a little box with little metal things that you would screw in and out. It would say, connect this one, connect this one, connect this one, connect this one, connect them together, blah, blah, blah. And it was, you know, it took a lot of time. You got, like, things stuck in your finger from doing it so many times. You know, I have, like, an SMA fingers. And, you know, and it was fairly error-prone. You had to be really careful because if you connected the wrong one or connected one and pushed the wrong button, obviously it would give you an erroneous result. Now they have electronic calibration modules. We call it an AutoCal, where it kind of does that all for you. So, you know, it's pretty hard to screw it up. It's not impossible, but it's pretty hard. Anyway, so it'll do that all for you. You connect those things. That's a connection here, and it does all that magically and calculates all the error coefficients. So then when you measure S11, it just does a ratio of these two. S22 is a ratio of these two. And then S21 is a ratio of the measure to the reference, or S12 is a ratio of the measure to the reference. So all said and done, you know, this is a VNA, and that's what's going on. So this is a 2-port VNA, and it looks like there's 4 connections. There's really only 2. One is the return path or ground, depending on who you're talking to, but it's ground, all said and done. But we make ones with more ports. So 2, 4, we have one I'm doing with a customer. It's 24 ports. So each port has 2 receivers, and they share a source. So pretty cool. Okay, so basics of S parameters. Again, this is a 2-port, not a 4-port device, although it looks like 4. But this is a return path. The B is the return path. So basically, anybody, what is, and raise your hand, if I'm sending a signal in here and then measuring what's coming back at port 1, what measurement is that? I said a hand. Hand? Yeah? Is 1? Okay. Here, have a whatever. Okay.
Question?
Yes.
These calibration kits,
Yes.
they screw right onto the end connector,
Uh-huh.
and they calibrate that port, right?
That's correct.
How often would you have to do that once you calibrate it, once the metal doesn't change its length?
Okay. That's a great question, and I'm going to give you a prize for that. Well, you can have it anyway. Yeah, sorry, I didn't have the microphone. So the question was, we'll repeat it. So basically, his question is, I do all this stuff, I connect it, short open load through, yada, yada, and I do a cal, and how long is that cal good for? Right? And it's a great question, and it depends. That's the answer. So, you know, what I recommend, again, it depends a lot on what you're doing. So like guys who are, for example, characterizing components. So they're generating S-parameter modeling files, really want utmost accuracy, right? So those guys typically, first off, I'll tell you they will calibrate in a more frequent interval, but the best thing to do is to have a verification device, okay? So we actually make verification kits, but it doesn't have to be a verification kit. But it's basically a device with a known S-parameter file or set, right? So what you want to do is, after you've done your cal, you look at something measure it, and does it look like it did before? Or does it look like the model data that I have that came with the kit? So in the case of a verification kit, I have all the S parameters for each component in that verification kit. So when I do a cal, when I'm done, I'll pull up the S parameter file for that device, and I'll put it on the screen. And then I'll put the measurement, and they should lay right on top of each other, right? So that's really what you should do. The main thing that changes things more than anything is temperature, other than like mucking with the connectors. I mean, really, if you loosen a connector or remove a cable, you definitely should always recalibrate. Yeah. It kind of depends on what you're doing. I mean, they're fairly equivalent. I'd say if you're doing time domain stuff, what are you characterizing? I guess is okay, such as okay. So in that case, I'd say they're fairly equivalent. The one thing that you do have to be a little cautious of in terms of the difference, if you're a signal integrity guy where you're caring about impedance as a function of distance, so something we can do with a VNA. So if you know what a TDR is, so what a TDR real simply does, instead of doing all this, it generates a square wave, samples the square wave, sends it down a transmission line, it reflects back one or multiple times, and from that I measure the time delay from when I sent it to when it comes back, and I can determine there was a mismatch there, right? So, so when you do that, I can basically get that same information from a VNA. So doing that normally with a TDR, I'd be looking at, is that line 50 ohms all the way along? What is the impedance as a function of distance? Right? So that time would tell me how far away that mismatch is in terms of length. But a VNA can do it with some math. But the one tricky thing is with a VNA, because it's mathematically generating that time domain response, it's possible to have a violation of what's called causality. So it basically means that you're getting a response before you've sent the signal. I know it's kind of a, but anyways, so that's if you're doing that, then talk to me. Okay, so that's S11. I send out a signal, and it comes back. And I mentioned these before, S22, S21, S12. So those are kind of the basic ones. And realize this is 2 ports. If you have, and this generates a 2x2 matrix, S parameter matrix. But obviously, I can have a 4-port. Guys who do differential measurements would have, instead of 2 in, 1 in, 1 out, they'd have 2 in, 2 out. That gives you a 4x4 matrix. And, we make one that's 24 ports, so that's like even bigger. Let's just leave it at that. So in terms of looking at on the VNA, so this is our plug for, that's our ZNB, real neat box, for measuring S parameters. So return loss, you can go into the menu and say, I want dB magnitude. I'm measuring S11, I've already established that. And I want dB mag, so I get return loss. I want input phase, so that's basically what's the phase of the signal that's reflected back. So that's where you would care if at my input, my thing was perfectly 180 degrees out of phase, it would cancel out my input, right? If it was perfectly out of phase, it would make my signal bigger, but probably distort it. Okay? I might want to look at input impedance on the Smith chart. So I'm going to talk a little bit about Smith chart later, but not in great detail. Unfortunately, people don't really use it as much anymore. VSWR, VSWR. Okay. So transmission measurements. So those were reflection measurements. And I was looking at S11, but it could just as soon be S22. So I can look at gain loss. So this is like frequency response. Okay, so here's a good question. Okay, so I have 5 more books. Who desperately wants a book? And hopefully it's less than 5 hands. It's not. So we're going to get these out, and if you're somebody who wants a book, make sure you give someone your name, and we'll try and send you one. Okay, so what was I going to ask? Oh, what kind of device is that? And you got to raise your hand. You already got one. Raise your hand. I need a hand. No. Good guess. No. Bam. Sorry. Yeah, that's a good point. I'll give you something else for a consolation prize. It's a bandpass filter. But he said, and that was a good, that's kind of a wise-ass answer. He said, but the bandpass filter the waveguide acts like a bandpass filter, so I'll give you a consolation for that one. I like wise-ass, that's good.
Why
Yeah.
You said that S22 could be the same as S11? Is that
It's basically, no, it's not. I'm sorry, I misunderstood. So it's the same type of measurement. So I'm looking at port 2 instead of port 1, but in terms of those things, it would look the same. Not exactly the same, but you know what I mean. Okay, so this is a bandpass filter. So you can see here, same thing, transmission phase. So what's the phase going through the device? Group delay. Okay, here's a tough one. Okay, I want to get rid of these books. So does anybody know why that thing's going up like a sawtooth? And I need a hand. No. You got it. You got a book. Okay, so I'll give you something else. Who wants a book?
I don't know the answer.
Okay, well, you can have it anyway. He's deferred his book to you. Sorry. Anyways, good answer. Thank you. It's phase wrapping. So, when you're going through a device, when you get to 180 degrees, it's going to jump up. So you can actually add delay. And if you buy a VNA, you get my personal time to come and entertain you for half a day or so, and I'll show you how to do all that stuff. I've worked with you before, so I can be fairly entertaining. Anyways, so typically you might want to measure ripple, like in a bandpass. So that's going to come from a standing wave, right? If there's a mismatch in there, it means some of that signal is getting reflected. And typically, if it's getting reflected, there's a phase difference between the incident and the reflected signals, and it's going to cause that ripple. Okay, so it's just showing you here. I send the blue one in. I get the brown, I don't know what color that is, back, and I'm going to, the resulting thing is going to be that VSWR. Okay? I'm sorry, this is the resulting VSWR. So you can see peaks in it. Okay, so polar formats. So another representation you can look at, and this is, I'd say, from my experience, this is more antenna guys do this, but not necessarily. If anybody else has any other experience, by all means speak up. But in my life, I haven't used the polar display a lot on a VNA, but you can show this. So reflection coefficient, there it is, and it'll show you there's amplitude and a phasor. Okay, and these circles, the red circles are constant magnitude, and the radial lines are constant phase. Okay. Polar shows reflection coefficient in the complex plane with a horizontal real axis and a vertical imaginary axis. Woohoo. Okay. Cartesian plots, and this is what you mostly look at. Rectangular diagrams used to display scalar quantities such as whatever, as a function of frequency. And most of what you look at with a VNA is as a function of frequency, although it could be other things. Like another example is as a function of power. If you want to look at what happens to my device as I crank up the power, you can also do that. And again, if you want to do weird stuff, talk to your account manager and I'll come and entertain you. Anyway, so Cartesian plot, so you see there's, this is real versus complex impedance. So it's showing you a point on there. So this is a common one for more gray-haired microwave engineers. Not to say it's not important to everybody, but the reality now is more of the components that you buy are already 50 ohms, so you're not going to have to match them. Like what historically people would do with a Smith chart is you'd take an amplifier, for example, and it would give you some points on a Smith chart, and you'd want to get those to 50 ohms to match to whatever your load is, or your input is. And so you can use the Smith chart to get from one impedance to another. And it'll tell you, like, what length of line do I need, what complex impedance, what real impedance. Okay? So if you look on here, and this is kind of the things you got to know about a Smith chart, is after you've done a calibration, assuming you did it correctly, if you put a short on here, ideally, if it was a perfect short, and this is going to lead to a question, you'd get a dot out here, okay? And if I put an open on, I'd get a dot here, and if I had a 50 ohms here. And then moving down, you see here I have more capacitive reactance, and then moving up, I have inductive reactance, and that's on these circles. So for a book, so I've done a cal, okay, and after I've done the cal, I put a short on there going out to 20 gigahertz, and I don't get a dot. Anybody have any idea why? Anyone? Ooh, I stumped them. I'm sorry? That's a good thought, but it's actually not. So a couple things. First off, it has some electrical length associated with it, right? So that length is a function of frequency, right? So as you change the frequency, that length changes. So you can actually add delay to that measurement and move it to more or less a dot. But so that's kind of the more general answer. But the reality is, more so than even that, is when I make any of these standards, do you think it's a perfect short from DC to 100 gigahertz? Like, I'd be retired if I could make that, right? That's a hard thing to make. So you make it something close to that, and then you measure the hell out of it, right? And you get some really accurate data. So when you send in your cal kit to get it calibrated, they're really, really accurately measuring what that thing is, there over frequency. So when you do the calibration, it isn't that it says, oh, that's a perfect short, and I get a reflection coefficient 1 and a phase of 180 from DC to daylight. It actually has measured data on it. So when it does the calibration, it's going to say, I put that on there, and I measure something, and after I measure it, what do I get? I know what the load is. The load is this data file, and I measure what's in between, and that generates my cal coefficients. So, do you have a book already? I'm going to give you one, because you tried. Yes. It's been a long time, but yeah. What's that? So typically, what you would do, sure, is when you measure a point, So if you measure something, just in the simplest case, so I measure and say my point, so I'm going to start with something really easy. If I measure a point here, right, then I want that to get to here, right, 50 ohms. So it'll tell you, first off, what that is, what that point is, but when you add delay to it, you can look and measure what this impedance is. So, like typically, if you hold on one sec. Circles. It's been a while since I've done this, so bear with me. So, what you can do is when you add these areas of arcs of constant reactance. So this is adding something that's a complex impedance, right? So I can move along this curve here by adding or subtracting some amount of capacitance or inductance. So moving down, if I want to move down, I'm going to add capacitive reactance. If I want to move up, I'm going to add inductive, right? So and the goal is basically to get you onto this circle, and then you're probably going to have to add some real impedance to it there, simply said. Yeah, I mean, broadband matching is another challenge. You basically have to do sort of stages of it where, that's a fairly complex topic. But yeah, in principle, what I just mentioned would be at a single frequency. To do a broadband match, you have to make some trade-off between the frequency ranges. So if you want more on that, I could definitely have some stuff I can give you. But okay, why do we use 50 ohms? Okay, so depending on who you're talking to and what they're doing, different groups have had different interests and different impedances. So over the years, if you look at load impedances, 77 ohms gives you minimum attenuation. Okay? So who uses 77 ohms? TV receivers, antenna lines actually use 75 ohms, which is obviously very close to 77. And the reason they use 75 is it's sort of an even multiple of 50, or an integer, fractional integer multiple of 50. 60 is the maximum voltage capability, but nobody uses that. 30 has the best power loading capacity for high transmitters, for example. 150 ohms is the minimum capacity per unit length. So low capacity test lines like sense heads on an ATE. And 50 ohms is sort of like, a compromise in between. And then 93 ohms is a compromise between alpha min and C min. So this is used in data communications. I know, I've had stuff in a past life where Intel did a lot of lines on a backplane that were 90 ohms. So, okay. So let's talk about some different types of components. Okay. So components, they basically change the signal or signal path. So they make it bigger, they make it smaller, they may clip it, they may, transduce it from like an antenna. And they typically talk about two different groups of components, active and passive. So passive are really things that you don't plug power into, all said and done, right? So attenuators, filters, mixers, usually. There are active mixers. What else? Balance, all kinds of crazy stuff. Anyways, and then active, more often than not, it's an amplifier. It could be a series of things. So, in the end, most people are designing a transmitter or receiver or both, a transceiver. So if you're designing a transceiver, there's all this stuff in there. So we'll just call that an active device. And, you may make some of the similar measurements that you would make on each component, but for the whole system. I mean, all said and done, whatever you're making, if you're a component guy, your component goes into a system, and that system has to work, right? So we go and we look over a link budget. What's a transmitter supposed to look like? Can I transmit enough power that looks correct, that can get received at the other end with the right amount of power, and I can decode it and take my information out of it. So in the end, that's really what we care about. So that's showing like a really high power amplifier. That looks like that's a Balun. I'm not going to even ask what that is because it says right there. That's an attenuator, like a higher power attenuator. And these are just adapters, changing one type of connector to another. And you can see here, these are actually what I would call metrology grade connectors. And you can see here, like the center pin there. Like often you'll see on a less expensive connector, where that center pin here, that's the pin, and that's the thing the pin goes into. And you'll see often this is white. So that's like a Teflon dielectric. So the dielectric material between the conductor and the outer ground shield may be a dielectric material. The better connectors, metrology grade connectors, are always air dielectric. They're much more precise. They're defined over a wider frequency range and much better performance. So if you're using a VNA, I always recommend you're using air dielectric adapters. Question?
That question of calibration before,
Uh-huh.
now that you're pointing it out, that's
Yep.
the most important part. So
Yes.
every time they make a new connection, they should examine the connectors
Yeah.
before they insert,
Yep.
because if that pin is damaged,
Yes, you're absolutely
you're
right.
going to get bad readings.
No, you're absolutely right. And I do have a couple slides on that. But, other than VNAs, a lot of this stuff isn't that big a deal. I mean, I have a lot of guys I work with who, they're measuring stuff on the spectrum analyzer and they really kind of care about, can I demodulate the signal? Do I get a decent error vector magnitude? And do I get about the right power? They don't really care, like, what's the VISWAR or whatever. And that, for them, they probably don't care. But if you want to accurately measure what's the phase response, what is the input match, what's the output match, reflection coefficient of my device, you really want nothing to make that measurement signal worse. So that's why you want to use really good connectors. But good point, thank you. Okay, so common components. Transmission lines we talked about, attenuators, filters, mixers. So mixers are really transforming one frequency to another. Couplers, I mentioned that in the VNA picture. It's sampling a bit of a signal off. Combiners, taking two signals, putting them together. Did I have a question back there, or are you just stretching? No? Okay. Circulators, basically making a signal go in one direction. Isolators, similar. Duplexers and diplexers, that's really like a multi-port filter. So like, for example, on a cell phone, the transmit and the receive frequencies are different, but you might want to go to a common port. So that transmit and receive go to two different things, and they both have different frequency ranges in those bandpass filters, but they have a common output port. And antennas we mentioned. So you see there's a lot more passive things that you typically worry about. And then the other one, it's not spelled out particularly, is cables, right? Cables are typically really, to really accurately measure, are one of the harder things to measure really accurately. Then common active components, PAs, LNAs, oscillators, variable attenuators. Okay? Okay, so active stuff we'll talk about first. So we'll just assume an amplifier for now. That's probably the most likely active device you would measure. So what would I measure on an amplifier? Well, I'm trying to make the signal bigger, and I should know, based on the designer specs of that device, what's the gain? How much bigger is the output than the input? So I want to measure it. What's the flatness over the band I want to use it over? does it compress? So when I put a signal in and I keep increasing the signal level, it should go out at the output or the input plus the gain, right? And at some point, that gain starts to drop off. Obviously, even though I have a part that says it has 10 dB gain, you can't put anything into it, right? If I have a little part like that and it has 10 dB of gain and I put like a kilowatt into it, it's not going to give you 10 kilowatts out. That should be fairly obvious, but it'll probably just melt the part. Anyways, so compression is basically at some point it's going to stop giving you output power. Harmonics, so when I put a 1 dB or 1 gig signal in, I'm going to get some 2 gig, some 3 gig, whatever. You're going to get harmonic signals. It's just the nature of the physics of whatever device you're making. And can you live with it depending on what you're doing? Intermodulation, so that's, I think if I have any slides on that, but intermods are basically, I'm putting in multiple signals or signal over a wider bandwidth, and those things mix together. And stuff that mixes far away, we don't really care about because we can always put a filter on there. But there's some math that happens where those two will mix and give you signals very close together that you can't filter out. So you need to be sure that your amplifier is able to put out enough power, not generating those intermodulation products. Okay, stability. Obviously, if you put in an amplifier, you want an amplifier, not an oscillator. So that's stability. Noise figure, and I'll talk about this in a little more detail, but it's basically, when I look at KTB, so thermal noise, that's as low as I can get, and I want to look at a signal above there, the reality is when I have an amplifier with some gain, it's not going to just amplify the signal. It's not a perfect device, so it's also going to add some noise too. So I want to characterize that and know how much that noise is added. Okay? And adjacent channel power. So a lot of times if using this, like for example in a cell system, the channels are defined, right? So I'm using it from here to here in frequency, but that thing might generate intermods or something that spill over into the next channel. So if I'm talking in this frequency, I don't want it to get into the guy next door. It'll ruin his sensitivity. Question?
Noise, what is it called? The dynamic range? What is it? The noise?
Yeah.
The range between the phase margin, it's called margin, right? Phase margin or the noise margin? Is that the stability measure?
So, yeah, right. Yeah. It has to do with that, yeah. I'm not going to get into that right now, though. Okay, so mixer types. So, and I've done lots of converter design in my past, but basically what a mixer does is you have two frequencies that you put in and you get one out, right? And this is showing the arrow going in here and in here. So this is what I would call a down converting mixer. So it's taking a high frequency and giving you out a low frequency. So basically I need two sources to test this part. I need an RF, a high frequency, an LO, probably a reasonably high frequency, and I get out a lower frequency. So, this is usually an integral part of most radios, particularly a super het radio, which is what the most common architecture. So most mixers, they'll work in the other direction too. So this puts in a high and gives you a low, but you can also put in a low and get a high. Okay? So the common uses of this, you'll have a fixed RF, which means that is just at a frequency, right? And then I'm moving the LO, so I'm changing that LO signal in frequency to get a varied IF. Okay? You might have a fixed LO and a swept RF and IF. So this is fixed, and then you're moving this. And up conversion means I'm going from a low to a high, so that's IF to RF. And down conversion is going from RF to IF. Any questions on that? Boom. You can. That's kind of another conversation, but the problem you have is it's called DC offset. so you get some error associated with that. So we've gotten pretty good at doing that now. It's kind of a different conversation, but it's a good question. Okay. So mixer testing. So I'm looking here on my ZNB analyzer. And so what type of measurements might I want to do on this mixer with a VNA? And there's some measurements that you're going to do here that you won't be able to do on a VNA. Boo. I'm a VNA guy. But you would use maybe a spectrum analyzer or something like that. Okay. So what are some of these measurements? So this is showing you a bandpass response of a mixer. So in reality, this is probably a mixer with a filter, but most of these things don't work from DC to daylight. They have some defined frequency range they work over. So some common measurements. I want to know what's the frequency range of all three of those signals. So when I measure the output, maybe I'll fix two of them and then vary one of them and see what happens. If I vary this one, what happens to this one? And probably it's going to go down over frequency. Okay. Then you have LO-IF isolation. So basically, my LO is kind of my signal I use to convert from a higher frequency to a lower frequency, or vice versa. And the LO isn't really typically a signal you want in the output, right? It's a signal you use to get that frequency conversion to happen, but you want it to go away when you're done, right? But some of it sort of leaks through. So one of the characteristics, if you look on a mixer data sheet, is LO to IF isolation, RF to IF isolation, RF to IF isolation, these two, and then there's RF to IF. So basically, signals bleed through that you don't particularly want to get there, and you have to be aware of those. So the challenge when you design stuff with mixers is you get lots of frequencies out, right? The thing where, did I do the math? No. So, typically you'll say IF is RF minus LO, right? Boom, I'm done, I'm happy, everything's good. So the unfortunate reality is that's not all you get. You get IF is also RF plus LO. You get 2RF minus LO, RF minus 2LO, blah, blah, blah. And so all the integer components, integer multiples of all those things will all show up, right? So when you figure out what frequencies to use and all that, you need to be really mindful of what frequencies you're picking, particularly for the LO, because that's usually the one you get to pick. Usually the RF is defined by, say, the standard. So if I'm doing cellular, the standard's going to say I'm at 700 meg. It's a LTE phone. So it's a 700 meg RF. My A to D is at 70 megahertz. So I'm going to go from 700 to 70, So can I do an RF minus LO? Should I do something else? And, when you pick those frequencies of the LO in particular, you want to make sure you know all the extra junk that gets through there, and is it going to be a problem, and can I filter it out? Because you're going to have a filter in here somewhere. Okay? So insertion loss, passband flatness, harmonics. Again, I mentioned harmonics, so you're going to get integer multiples of everything. When you look at the output of a mixer, you see lots of stuff. It's not fun. And often when you design a system, you're going to take a mixer, put some stuff before it and after it, then you're going to put another mixer in. And in some cases, I did a system that had 3 mixers. And, there's filters in between, but stuff still leaks through, right, at some level. So you've got to be really planning your frequencies very carefully. Okay, so connectors. Kind of mentioned some stuff in passing, but connectors, they're obviously everywhere. And as was mentioned, it was a great comment, you really need to look at the connector before you connect it, right? These get dirty. People throw them in a little box with a bunch of other crap. You get lint in there. They get bent. and it will degrade your signal dramatically if it's damaged or dirty. So always look at them. Ideally, you'd look under a microscope. Not that I do that, but in principle. So yeah, it should be regularly cleaned. And as I mentioned earlier, every connector causes a mismatch. If you go and look at connectors, adapters, whatever, they will have a spec for VisWare on them. And you'd be amazed. You'll see ones that are 1.05 and you'll see ones that are 1.5. If it's 1.5, it's not very good. I bet you it doesn't cost much. You can probably get it at Fry's. Question, comment?
What's the difference between SMA and 3.5?
That's a great question. I'd give you a book if you didn't have a Rohde shirt on. Okay, so SMA is not a precision connector. So the common thing with an SMA, if you look at it, you'll see a white stuff with a little metal thing in the middle, right? So that conductor in the middle, it's basically, more often than not, somebody gets a piece of coax and they strip off the ground shield and they stick a connector on the end, right? So you might imagine that doesn't make a very precisely tolerance and all that. So if you're going to connect it once and never again, it might be okay. I'm a VNA guy, so I doesn't work for me, but it's a very imprecise connection. Typically has undefined specs, so highly unrecommended, particularly with VNA measurements. 3.5 is a precision connector, so it has an air dielectric. It doesn't have the white stuff there. It's an air dielectric and very precisely machined tolerances. Guess what? They cost more. Your manager probably doesn't like that. They'd say, buy the SMA. I like the cheaper ones, but it's got to work. So anyways, so if you look at the specs on them, there's a spec for a 3.5 millimeter connector in terms of frequency range, VisWare, and all that. I think it goes up to 26.5, just off the top of my head. SMA, you'll see stuff where they'll say 18 gig. It depends. It's not a standard. Go ahead, question.
You also got the screwed up reverse polarity SMA, so you're not careful.
Yeah, that's a good point. Really good point. Yeah, and that's a really great point. And it also leads me to just a general comment with this stuff, particularly on a VNA, is know what all your connections and cables and all that stuff are. Surprisingly, I had a guy I worked with who, some of these connectors are compatible with each other, right? We're going to just forget about SMA for now, because that's a dirty word for me. But 3.5 and 292, 3.5 is 26.5 gigahertz, 292 is 40 gigahertz, right? So those two, you can actually mate them together. It's okay to connect them, screw them, unscrew them, whatever. Just make sure you torque them, and I'll make some other comments on that. But those two are allowed to connect. And it's not on here, but there's also a 1.85, so 2.4. So basically, that's a 26.5 gig connector. That's a 40 gig connector. That's a 50 gig connector. Then there's a 1.85, which is a 67 gig connector. So you can take a 2.4 and a 1.85 and bolt them together. They will mate. It's okay to do it. It won't damage anything. You can take a 3.5 and a 2.92, and they will mate, and it's okay to connect them together. Obviously, you only get the guaranteed performance of the lower frequency connector, but it'll work, right? If you only want to go up to 26.5 gig and your thing is 2.92, it's fine. Bolt them together, but just don't expect it to work automatically up to 40 gig. SMA, so it will technically mate with these two, but you got to be really careful because you can really damage those. N-type, that's the big one, usually up to 18 gig. Higher power is really primarily why people use that, although it's much more rugged. It's the most rugged of these. SMC, not going to comment a lot on that. BNC, this is typically I forget what the upper frequency spec is on BNC, but typically you look at like reference signals, clock signals, a lot of the scope stuff. Is my scope brethren here? No. So I can make wise scope cracks. Anyway, so, scopes up until, they got up into microwave range and stuff, typically had BNCs on them. But they're typically, not the actual test connector. So anyways, and you see here there's adapters, so you can go from one thing to another, but just be careful. Yeah, I think I started saying this, but I had a guy, we had a 2.4 millimeter VNA, so 50 gigahertz, and a 3.5 3.5 and a 2.4 do not mate. If you try to screw them together, they won't mate. But apparently, if you try hard enough, you can make them mate. It's good for one insertion. The performance is really bad. We'll say it's not repeatable, so don't do that. But it's okay for us, because then we get to fix your thing and make you happy again.
Question?
Yes.
You're saying that the thread pitch on all, like the SMA, the 3.5, it's the same exact thread?
No. So what I'm saying is these two will thread, right? And this one and the 185 will thread.
Did you say the SMA will also thread?
SMA technically will, but again, this isn't a precision connector. So, it does happen where you plug this into this and it damages it. Like more often than not, what happens is that center pin, because it's not a precise toleranced center pin, it might be offset and not go in here correctly and then bend the pin.
When you buy super high quality SMA cables,
That's an oxymoron, by the way.
they're very expensive. Do they not put a dedicated pin in?
Well, I mean, if you're buying an SMA cable, it's not very expensive. I'll tell you that right now. If you're buying a 3.5 millimeter connector or cable, it's expensive. If you're buying an SMA cable, it's not expensive.
How much would the patch cost for the?
So, I mean, like we have some out. Actually, no, I have the really, really good ones out there. So, like a Goreflex, which is kind of the best cable you can buy, 1 meter, 3.5 millimeter. I don't know, it's $1,000.
Gee, I'm going to steal it.
Yeah, I mean, but you can go buy one that has SMAs at Fry's for $15, right? They don't have the same performance. I'm not suggesting you need to buy the $1,000 cable. There's something in between. I mean, like I do a lot of stuff with some other companies who make cables. Jinkosha comes to mind. And they make high quality, 3.5 millimeter cable, and it might be $200-300. That's probably a reasonable amount to pay to actually do it correctly. Yeah. But if you ever call me and I help you and you have shitty cables, I'm going to give you a hard time. Any other questions? Okay. Yeah, go ahead.
You should add the little micro connectors, UFLs, and everything else to this too, because everybody's migrating.
Yeah, it's a good point. I mean, the only thing is a lot of those. So I'm familiar with all of them. I don't know the specs on a lot of them, and I don't think any of those are precision connectors. I mean, I think MMCX might be, but like you don't typically see even a cal kit for those, right? No, I know what you're saying. I know what you're saying. I know. Yeah, it's a valid point. I don't get to make that decision. So, anyways, but valid point. Okay. So what's next? So connectors, starting with the coax. Like, I doubt anyone here is going to actually manufacture a cable. If you are, whatever. Designing a cable, gives you the cutoff frequency for a coax cable. It has to do with the center conductor, the dielectric, the spacing, etc. So when you go home and try to make a coax cable in your garage, that's how you do it. But don't call me. So those are the dimensions you would typically see. Okay. So, the reason we beat these to death in terms of connector types is because people always use the wrong ones. They'll say, I have an SMA cable. I had a guy at a digital company. He had a thing, it was an SMA cable, and he was trying to measure something at 110 gigahertz. And guess what? It didn't work for squat. So, that's the 1 millimeter connector. So one of these guys, I had to buy a bullet for doing a calibration of a 1 millimeter connector. So just one little part was $2,000. Probably, maybe could get cheaper ones, but when you go up here, this is kind of like an exponential curve. You can see that's the price going up like that. So, anyways, yeah, once you get above 3.5 millimeter. So 3.5 millimeter goes to 33 gig. I think I said 26.5. So, anyways, so we like it when people buy stuff up here because it makes my account manager friends happy, so they can make quota. Anyways, so one thing just to mention on our instruments, not a VNA. We have this adapter system. So that little thing there, basically, this is not an N connector. That is so when some guy has one of these on the front panel of their instrument, and then they try to, bolt something on with a pipe wrench, and they mess up the connector, then I can come in and be the hero and take that off and put a new one in, and then you can go on your merry way. Maybe charge you a couple $1,000. But so that's kind of like a connector saver, I guess, for a friend of a spec N, but we only do that for N-type. So these are all the connectors on the front panel of our various instruments. So N-type, 18 gig, 3.5 millimeter, 26.5 gig, 292 to 40 gig, 24 to 50 gig, and 185 to 67, and I probably should add it on here, but we also have instruments that have the 1 millimeter that goes up to 110. Like we have a VNA that'll go to 110. You can actually go higher than that. If you want to go higher than that, it's a waveguide. So we have a VNA that'll go up to a terahertz. So like Stanford has stuff like that. Anyways. And these are all ruggedized so that you can make lots and lots of insertions. That's really the intent of kind of metrology grade connectors is you're going to make lots of insertions, and it's very, very repeatable over lots and lots of insertions. Okay. That's the simulated threading a connector. So if you kind of look at what's going on inside here, the intent of this thing is that's the female connector, and this goes over this when you thread it in, and you'll see in the next picture how it's supposed to look. But one key thing to remember is when you connect these, and it's if you're using an SMA, I don't really care what you do. Well, no, that's not true. So if you're when you're connecting the male connector that has the nut that spins, that's the one you always turn. Don't turn the other one. That's how you'll degrade the outer conductor of it. So for example, some of the better connectors you'll see, this is gold plated. So it has some thickness of gold on it. So when you don't spin it correctly, you're going to scrape off some of that gold. So turn the nut, not the thing. So this is the established reference plane after you make the connection. And as I was pointing out, when you connect it, if it's a good connector and it's not damaged, that's what it should look like. So you see you get that mating surface here that's flat over that distance. If it's damaged or it's an SMA connector, you're going to get something like this, where you don't get the same degree there. And this obviously isn't as repeatable. When you see it's kind of bent like that, you're going to see every time you connect it, this isn't going to look the same, right? This may be touching down here instead of here, or it may rotate. So if you looked at the Viswar or whatever, it's going to look different every time you reconnect it. So that's why you care. If you use a good connector, that mating surface is going to be along the entire threaded portion right up into where they butt together. What's that? How to detect that? Well, so the main thing, you can't really see this once it's connected because obviously it's threaded. But if you look at this here, the center pin, you see there's like 4 little slots. So you should look at it. If you looked at it carefully or under a microscope, I'm blind so I can't see squat. But that thing should be pretty much tight right together. Those spaces should be minimal on all 4 of those spaces. And if you see, like, sometimes one of these might be bent back a little bit or the spacing is different, that's when you go, yeah, maybe this connector's damaged. Yeah. So align it. So you'll find, obviously, when you connect these things, you can put it in crooked, and obviously it won't thread. Hand connect, so start turning this guy, not this guy. Okay, and if you feel resistance, like it's not connecting properly, then stop and back up. Like what I often do is, when you connect it, if you start going backwards, you'll feel a little click, and then you go forwards, and then it'll go in. Okay, and then torque it. And again, this is especially for VNA stuff. See, there's a Cal standard on there. So the Cal standards you'll even find, like particularly if you get above probably 18 gig, if you don't torque them, you're not going to have a repeatable calibration. Okay, kind of beating this to death. Here's a bunch of different wrenches and what the torques is. So I'm not going to quiz you on that because I don't even remember them. So, keep them clean. Ideally, you put caps on the end. We all have that. If they're SMAs, I don't care. Don't leave them lying around to get dirty. Yeah, don't put them face down, too, because you get stuff in there. And guess what? We have an app note on that, too. Okay. Any questions, comments, concerns?
Can you see the difference between a 3.5 millimeter and SMA if you look at them under microscope?
On an SMA, you can because the SMA is white, right? That one's easy. Like difference between like a 2.4, 2.9, 2.4, 2.92, 3.5, 1.85, it's pretty hard to tell. I mean, typically what you'll see is like if you look at the male side, I can't tell on the female. My vision's not that great, but if you look on the male side of it, you'll see the spacing between where the center pin is, and there's kind of like a little flat part right back where. Let's see if it shows it in here somewhere. So, yeah, here you'll see. This is such a close-up, but you'll see the spacing is closer to the center pin. It's pretty hard to tell, but if you look at them enough times, you will. But telling between like a 2.4 and a 1.85, I can't really tell. But I can tell like a 2.4 and a 3.5 kind of thing. And it's okay to kind of put it on there and try it a little bit. But if it doesn't go, then it's probably wrong. That would be I've done that myself.